B is the solid where 0 is less than or equal to z, which is less than or equal to y squared. Minus 1 is less than or equal to y is less than or equal to 0. And 0 is between 0 and 1. We're asked to set up triple integrals that will find the volume of this region in space using every possible order of integration. That's 6 things. So let's think about it. I can use z as my first variable of integration, and then one possibility would be then to use y and then x, but I could just as likely choose x and then y. Next up, I could integrate first with respect to y, and then with respect to z and x. Keeping with y first, I could then go x, z. Finally, the two different options for integrating with respect to x first, choose y and then z, or choose z and then y. So I'm going to set up 6 different triple integrals for this problem. And hopefully it won't be that bad. It won't be that much work. My first job, no matter what order of integration I'm going to choose, is to sketch the region B. So that's what I'm going to try to do next. I'm going to try to draw the region in space that is bound by these 3 inequalities. So 0 is less than or equal to z is less than or equal to y squared. Well, just for a second, if I think about that in a y-z plane, z equals y squared, well, that would look like a parabola. And then I get a little bit more information. I know that y is between -1 and 0, so it's really just this piece. Trying to sketch this graph, I already kind of have the idea of what it would look like projected into the YZ plane. I guess in this perspective, the x-axis is coming out of the board, and this would just stretch along that. So look at this like little wedge-shaped area. Let's see if I can, volume, this region in space. Let's see if I can draw that. So an x-axis, a z-axis, and a y-axis where I'm going to need some of its values back here. If I think about this point I was thinking about here in a thought bubble I didn't even draw, I plug in -1 for y, I get out 1 for z. So let's see if we can sketch that little parabolic piece in. And it would look something like that. So that's that region I drew there. And now I need to drag it along the x-axis until it's at that point there. So and it would look like a little parabola there too. And so I get this thing that looks like a ramp, like part of a half pipe, or a curvy doorstop. And that's not the best picture in the world, but it'll work for our purposes. But I thought, since I have to draw this a whole lot and think about rays passing through the region, I actually have some computer printouts. And the computer didn't do a great job printing out these points, but that's okay, as long as we can see the region there. And so there's the parabola, and then imagine stretching that out to this point at x equals 1, y equals -1, and z equals 0. And so let's see if we can, let's do these two first. Integrate with respect to z first, and then y, and then x, and then we'll go z, x, y. So in both of these, I need to draw the same projection of the region into the xy plane. And well, I see that plainly, if you will pardon the pun, as being this square. And so I have B there, and now I have the region R that I like to think about in the XY plane. And that's nice to realize that for these two orders of integration, since these are going first, the projection plane's the same. It doesn't matter what order I did them in to determine that plane. All right, so here I'm out at x equals 1. And here I'm at -1 on the y-axis, so it's this square here. And so there's my region R that should help me find bounds for the second and third bounds for this integral. So now my job is to draw a ray through the region perpendicular to that square on the bottom that's parallel to the z-axis. And since I have a good picture here, I have a little better shot at drawing something that actually is parallel and perpendicular to the right thing. So I'm traveling in the z direction, and I hit that square, and then I come up and I hit the surface itself. And so if I think about it, when I hit the bottom there, kind of the floor of this wedge, that's at z equals 0. And then very clearly here, that's at z equals y squared. And so integrating with respect to z first, I now know bounds in the z direction. And since I've only drawn that ray, I've really gotten the first step on the first two orders of integration. All right, so now I only need to concern myself with the projection region R. In this first one, I need to draw a ray through my region parallel to the y-axis, perpendicular to the x-axis. And I can see that I enter the region at y equals 0, and I exit at y, enter at y equals -1, and I exit at y equals 0. Okay, and now I need bounds for x that contain the entire region, and that's from 0 to 1. And since I found the second bounds on that one, I think you should pause the video here and see if you can fill in the rest of the information here. Okay, so now I'll fill in the rest of the information, this time integrating next with respect to x. I enter at x equals 0, and I exit at x equals 1. And now I need values for y that contain the whole region, and that's from -1 to 0. And what I realize is that if I did one round of integration here, then the next two are over a rectangle, over a square. So Fubini's theorem says I could just swap those. And so I literally see a 3D use of Fubini's theorem. But we have our first two orders of integration. We're 1/3 of the way through our problem. So now I want to think about the next two orders of integration. First, integrating with respect to y, and then z and x, and then x and z. And just so I don't forget which orders I've said I'll do, I'm going to go on and put in places here to write all of my answers down. Okay. So, again, my first step would be to draw the region. My next step would be to draw the projection into what is the xz plane. And so I imagine that I flatten this down, or that I'm looking down the y-axis, and I would see that square in the back, right? So I'm imagining projecting it into the xz plane, and it would look something like this. And I can see that in the x and z direction, these bounds are really nice, and that this would just be the point 1, 1. Then I'm just dealing with a 1-by-1 square there, and so my space region B, the projection into the xz plane, that's my region R. All right, so I need to send a ray through region B, perpendicular to that square, which technically is out here, but we can think of it as the back wall there if we'd like, and parallel to the y-axis. So we'd be traveling in the y direction. We'd strike what I'm thinking of as the back wall, and then come out and hit the front of the half pipe or doorstop shape that we're dealing with there. And so what I realize now is that is going to happen back there where y is equal to -1, and here I need to solve this equation. Z equals y squared for y. Well, if I do that, I get z equals plus or minus the square root, y equals plus or minus the square root of z, and I'm definitely on the negative side of the y-axis, right? Y was told me from the very beginning to be between -1 and 0, and so that lets me write down that top bound, and since that works for both of these, I'll go on and write that in there. Okay, so now let's see if we can find bounds in the next two orders of integration, z and then x, x and then z. Pause the video here and see if you can get ahead of me and write those down. Okay, so I need to draw a ray through this square first in the direction of z. Now, I probably don't even need to do this because that's clearly a square, and we can really see what's going on. So I have a feeling a lot of you might have just done this very quickly. And now I need bounds for x that contain the whole region, and that is from 0 to 1. Well, again, I could think about Frobenius theorem. This is a square. This is very boring, right? Here, x. Here I have the line z equals 0, and excuse me, x equals 0 and x equals 1. I got ahead of myself or behind myself there, and I get those two integrals. All right, so now we're 1/3 of the way there. We've written down, excuse me, 2/3 of the way there. We've written down 4 of the possible 6 orders. These are the only 2 that are left. I need to find bounds in the order dx, dy, dz, and in the order dx, dz, dy. Okay, so I now need to draw a projection into the y-z plane, and this is the interesting one, right? If I think about shining a light down the x-axis, this shadow here is actually where we started our conversation about drawing this. It's that kind of parabolic region back there. All right, so now I need to draw a ray through that region, perpendicular to that back wall, parallel to the x-axis. So I'm imagining traveling along that direction, hitting that back wall, traveling through the region, and coming out through this front wall that has the same shape as the back wall. Okay, so what would those be? Well, even though I have that nice parabolic shape to it, that's still just happening where x is 0 and then x is 1. Right, those are just parts of the planes at x equals 0 and x equals 1. So those bounds aren't that interesting. Now here is where the bounds can be interesting. I first need to think about this region, which is the region R. And this says first with respect to y, so I'm going to draw a ray through that region in increasing order of y. And if I do that, I enter at the line y equals -1, and I exit at that parabola. And that parabola is z equals y squared. So I need to solve that again for y. All right, and now I need bounds for z that contain the whole region. Well, that's between 0 and 1. One more order of integration to go. Now I need to draw a ray through this region in increasing direction of z. I would go into the region at z equals 0, and I would exit the region at z equals y squared, and now I need bounds for y, and those would be from -1 to 0. And now we've found 6 different triple integrals that would evaluate the same volume. What I think you should do now is pick any one of them to actually evaluate, to do the iterated integration and find the actual volume of this half-pipe shaped region.